What if I told you that right now, hidden within the objects you touch every day, entire invisible worlds are constantly in motion? Worlds so small, so breathtaking, they would stop you cold if you could ever see them. Welcome to Micro-Worldsthe, the chemistry of everything. This is where we venture past the limits of human sight and descend into the molecular architecture of reality itself. Through extreme macro and microscopic cinematography, we reveal the hidden engineering happening at scales 1,000 times smaller than a human hair. Every object you own, every bite of food, every screen you tap, every pill you swallow, is the result of nature's most sophisticated chemistry, playing out in complete silence. Today, we explore three of humanity's most remarkable creations: chocolate, smartphone screens, and pharmaceutical drugs. Each one a masterpiece of molecular engineering. By the end of this video, you will never look at the ordinary world the same way again. Let's descend into the invisible. Chocolate. For most of us, it is simply pleasure. But at the molecular level, it is one of the most chemically complex foods on Earth, with over 600 distinct flavor compounds locked inside. This is a single cacao bean magnified 500 times. What looks like rough brown terrain is actually a dense forest of protein structures and fat globules locked together in crystalline layers. The journey begins with fermentation. As cacao beans are piled and left to heat, yeast and bacteria begin dismantling the sugars. What you are seeing is acetic acid forming, molecule by molecule, in real time. Now we enter the roaster. At 140 degrees Celsius, the Maillard reaction ignites. Amino acids and sugars collide at incredible speed, generating hundreds of aromatic compounds that give chocolate its signature scent. After roasting, the nibs are ground into chocolate liquor and then conked, agitated for hours. Watch as the microscope reveals jagged cacao particles being steadily worn into smooth, rounded spheres. Now for the most critical step: tempering. This is where chemistry becomes art. Chocolate must be heated, cooled, and reheated within precise temperature windows, measured to fractions of a single degree. Cocoa butter can crystallize in 6 different forms. Each form has a different structure, a different melting point, a different texture. Most are wrong. Only one form is perfect, Form 5. This is Form 5, seen here under polarized light microscopy. Notice the tight, uniform lattice of fat crystals, perfectly arranged in compact beta-prime structures. This geometry is what gives premium chocolate its sharp, satisfying snap. Lecithin molecules are added to the molten chocolate. Amphiphilic by nature, each molecule has one end that loves water and one that loves fat, acting as a bridge, smoothing the texture into what we recognize as silk. As the chocolate sets and cools, volatile aromatic compounds begin to escape: theobromine, pyrazines, aldehydes. Each molecule drifts upward to your nose, triggering the cascade of signals your brain interprets as craving. What you are seeing now is a cross-section of finished, dark chocolate at the micron scale. A precise mosaic of fat crystals, cacao particles, and sugar matrices, all held in elegant equilibrium. From ancient beans to molecular perfection. Now let's shift to something born in a laboratory, an object that lives in your hand and speaks to the world. The smartphone screen. The screen you're watching this on right now is one of the most precisely engineered objects ever created by humans. Its construction happens at a scale that makes individual atoms visible. It begins with silicon, melted, spun, and pulled into perfect cylindrical ingots. Sliced into wafers thinner than a human hair, the surface you see here is smoother than any natural object on Earth. Ultraviolet light is fired through a mask onto the silicon surface coated in photoresist. Circuits are etched with features just 5 nanometers wide, smaller than 20 silicon atoms placed side by side. Modern displays use organic light-emitting diodes, OLEDs. Each pixel is a stack of organic molecular layers so thin that if you scaled them up to the size of a book, the entire stack would still be invisible to the naked eye. These are the organic semiconductor molecules, carbon ring structures painstakingly deposited in a vacuum chamber. When electricity flows, electrons and holes meet, annihilate, and release energy as visible light. Here you can see a single OLED pixel at maximum zoom. Red, green, and blue subpixels cluster together, each firing at precisely controlled intensities to produce the millions of colors your eyes interpret as a photograph. The transparent electrode layer, indium tin oxide, conducts electricity while remaining perfectly clear. At this magnification, you can see its amorphous grain structure, a glassy arrangement of indium, tin, and oxygen atoms. The touch-sensitive layer is a grid of capacitors, tiny electrical fields that detect the change in charge caused by the approach of your fingertip. Each intersection of the grid is a single, independent sensing node. Color filter arrays sit above each subpixel, thin dye molecules that absorb all wavelengths of light except the one they are assigned to transmit. Their selection is precise to within a single nanometer of wavelength. The outermost layer is an anti-reflective coating, a gradient of refractive indices so precisely tuned that light waves cancel each other out before they can bounce back into your eyes. Reflections vanish into darkness. Gorilla Glass is chemically strengthened by immersing it in molten potassium salt. Larger potassium ions force their way into the glass matrix, replacing smaller sodium ions and creating a surface under immense compressive stress. Billions of these screens exist, and each one is a monument to molecular precision. Now we turn to something even more intimate: the drugs that enter our bloodstream and reshape the chemistry of our bodies. Pharmaceutical drugs are molecules designed with surgical precision. The difference between a medicine and a poison is often just one atom, placed in the right position, with the right shape, at the right time. In pharmaceutical chemistry, molecules are built step by step, like assembling a machine one bolt at a time. Each reaction must proceed with near-perfect selectivity. A misplaced bond can render a drug useless or even dangerous. Under polarized microscopy, crystallized drug compounds reveal their true architecture: ordered lattices of molecules stacked in repeating geometric patterns. The shape of this crystal directly determines how the drug behaves in the body. Many drugs can exist in multiple crystal forms. Polymorphs. Ritonavir, an antiviral drug, once failed when a more stable polymorph spontaneously emerged, making it insoluble and ineffective. The crystal structure of a drug is a matter of life and death. Here we see a computer simulation rendered from crystallographic data, a drug molecule fitting into its protein receptor like a key into a lock. The binding is driven by van der Waals forces, hydrogen bonds, and hydrophobic interactions. The active molecule is just the beginning. Tablet manufacturing requires binding agents, disintegrants, lubricants, and fillers, each serving a precise function. The tablet must hold together during transport, yet dissolve rapidly in stomach acid. Tablets are tumbled in coating drums as polymer solutions are misted over them. The coating you see forming here controls the rate of dissolution, engineering the precise window during which the drug is released into the bloodstream. When a coated tablet enters stomach acid, the polymer begins to swell. At the microscale, you can watch individual polymer chains uncoiling as water molecules penetrate, the tablet slowly surrendering its cargo molecule by molecule. Not every drug molecule that enters the body reaches its target. The liver metabolizes many drugs before they can act. Chemists engineer molecular features specifically to protect drugs from this first-pass effect, building tiny chemical shields into the molecule itself. The frontier of drug delivery is nanotechnology. Lipid nanoparticles, the same technology used in messenger RNA vaccines, encase drug molecules in fat envelopes just 100 nanometers in diameter, protecting them on their journey into the cell. Nanoparticles can be decorated with targeting molecules, antibodies or peptides, that seek out specific cell types. Tumor cells overexpress certain receptors, and these molecular scouts recognize and bind to them with extraordinary specificity. From crystal lattice to cell membrane, the journey of a single drug molecule spans chemistry, physics, and biology. Now let's pull back and look at the hidden structure of the materials that build our world. The materials that surround us are not static. At the atomic scale, they are dynamic, vibrating, shifting, reacting. Every surface you touch conceals a hidden, microscopic universe of extraordinary complexity. Glass begins as silicon dioxide, ordinary sand. Under the electron microscope, you can see its amorphous structure. Silicon and oxygen atoms arranged not in a crystal, but in a random, tangled network that somehow remains rigid. When silica melts at over 1700 degrees Celsius, the rigid network dissolves into a fluid of mobile silicon-oxygen chains. As it cools, the chains slow and lock, but never arrange into crystals. Glass is a frozen liquid caught mid-motion. Steel is iron mixed with carbon, a relationship that produces structures of astonishing complexity. Under the optical microscope, the grains of steel reveal themselves, individual crystalline domains, each oriented in a different direction. Where two steel grains meet, a grain boundary forms, a thin zone of atomic disorder that determines the material's strength, toughness, and fatigue resistance. Heat treatment can shrink or grow these grains, tuning the metal's behavior precisely. Rust is iron surrendering its electrons to oxygen, an electrochemical reaction that begins at surface defects too small to see. Here you can watch iron hydroxide crystals nucleate and grow, layer by layer consuming the metal beneath. Titanium can be anodized, immersed in electrolyte and subjected to voltage, causing an oxide layer to grow on its surface. The thickness of this layer determines which wavelengths of light interfere, producing the vivid iridescent colors you see. Diamond is pure carbon, but the geometry of its atomic bonds makes it the hardest natural material on Earth. Each carbon